People ask, how are magnets made? That sounds simple, but it isn't. Because the real mystery is not how we make magnets. The mystery is why matter agrees to behave this way at all. Take a piece of iron. It looks ordinary, quiet, dead, but inside it billions of electrons are moving, not randomly, not politely, spinning like tiny charged tops. Each one produces a magnetic effect. On their own, they cancel each other out. Chaos. No magnet. So here's the first rule you must understand. Nature prefers disorder. Random motion is the default. Alignment is rare. A magnet is not born when electrons exist. Electrons exist everywhere. A magnet is born when order defeats randomness. When we make a magnet, we don't inject magnetism into the material. That idea is childish. We force the internal spins to agree by stroking iron with a magnetic field, by placing it in a strong field, or by manufacturing alloys designed to resist chaos. We give electrons a reason, not a desire, to line up. And once they line up, something remarkable happens. The material begins to enforce that order on itself. That's the shocking part. The magnet is not held together by glue or force. It's held together by rules, invisible rules. You can break the magnet in half. Congratulations, you now have two magnets, not one magnet with a missing piece, two complete ones. Why? Because magnetism is not stored in an object like water in a bottle. It's a pattern. And patterns don't disappear when you cut them. They repeat. Heat the magnet enough and the order collapses. The electrons panic. Random motion wins. The magnet dies. Not because magnetism left, but because discipline did. So how are magnets made? They are made when matter is forced into obedience, when invisible motion is aligned, when chaos is briefly defeated. And that should bother you, because it means the world you see is not governed by what you touch, but by what you cannot see, cannot feel, and barely understand. A magnet doesn't prove human intelligence. It exposes its limits. We can make one, we can use one, but when we ask why nature allows this strange order to exist at all, we are still guessing, and that's the real lesson. Magnetism is not a thing, it's a consequence. That sentence should make you uncomfortable, because the moment you think magnetism is a thing, you stop thinking. You imagine it as a substance, a force stored inside objects, something you can pour in or take out. That picture is wrong, completely wrong, and nature punishes wrong pictures by confusing you later. Nothing in a magnet says, I am magnetism. There is no magnetic fluid, no hidden glue, no tiny North Pole particles marching in formation. What you see as magnetism is what happens when matter obeys certain rules. Rules it did not invent and cannot break. Inside every piece of iron are electrons. That much is ordinary, but electrons do something strange. They spin. Not like a spinning ball, don't imagine that, but in a way that produces a tiny magnetic effect. One electron is weak, meaningless. A billion of them, all pointing in random directions, still mean nothing. Chaos cancels itself. This is the first brutal fact. Nature defaults to disorder. If nothing interferes, the spins point everywhere. The material is not a magnet. It never will be. Not because magnetism is missing, but because order is missing. So when we say making a magnet, we are already lying. We are not creating anything new. We are not adding magnetism. We are forcing agreement. We are bullying nature into alignment. Apply an external magnetic field, and suddenly electrons face a choice they didn't have before. Align and lower the energy, or resist and lose. Many resist, some align. But when enough align, something remarkable happens. The aligned electrons make it easier for others to align. Order feeds on itself. That's not magic. That's consequence. The material doesn't want to be magnetic. Desire has nothing to do with physics. The system simply discovers that one configuration costs less energy than another. Nature is cheap. It always chooses the cheapest option available. And once that alignment stabilizes, the object behaves in a way that shocks beginners. It attracts iron, deflects compasses, resists being erased. Not because it stores magnetism, but because it maintains a pattern. Break the magnet in half. You expect one north and one south, right? Wrong. You get two magnets. Break them again. Still magnets, over and over. Because you never destroyed magnetism. You only copied the pattern into smaller regions. That should scare you a little, because it means what you experience as a force acting across empty space is really the visible shadow of invisible motion. You'd never touch magnetism. You only witness its consequences. Heat the magnet and watch what happens. As temperature rises, electrons vibrate more violently. Random motion increases. Alignment weakens. At a certain point, the pattern collapses completely. The magnet disappears. Where did the magnetism go? Nowhere. It never went anywhere because it was never a thing. The order died, and with it the behavior you named magnetism. This is where most explanations fail. They stop at because electrons align and call it understanding. That's lazy. The deeper question is, why does alignment of microscopic spins affect objects centimeters away? Why does nature allow local order to create distant effects? That question has no comfortable answer. We can calculate the fields, we can predict the forces, we can build machines that depend on them. But the underlying rule, the reason the universe is built this way instead of another, remains untouched. And that's the point. Magnetism humiliates arrogance. It reminds you that knowing equations is not the same as knowing why the world obeys them. You can describe the consequence perfectly and still not understand the causes, so stop asking how magnets are made as if they are manufactured like chairs or engines. Ask instead what kind of universe permits invisible motion to produce visible certainty. Ask why order, once established, can dominate space around it. Ask why nature allows patterns to act like power. Because magnetism is not a thing you hold in your hand. It is evidence that reality is governed not by objects, but by relationships, not by substances, but by rules. N. Not by what you see, but by what you never will. And if that doesn't make you pause, then you weren't really listening. Order is rare in nature. Magnets are organized rebellion. If you think nature likes order, you've been fooled by your own expectations. The universe does not wake up every morning trying to be neat. Left alone, things spread out, mix, decay, and fall apart. Heat flows from hot to cold. Structures collapse. Motion becomes noise. Disorder is not an accident. It is the default. This is not philosophy. It is physics. Every system, if given time and freedom, moves toward randomness. That tendency has a name, but names are cheap. What matters is the rule. Order costs energy. Maintaining it requires resistance. And resistance is rare. Now look at a magnet. It doesn't look rebellious. It sits quietly on a table, pulling paper clips like a well-behaved object. But inside, something unnatural is happening. Something that should not persist. Inside the material, countless electrons are in motion, each with a tiny magnetic influence. If nature had its way, and most of the time it does, those influences would point in all directions. They would cancel out. Nothing special would happen. No magnet, no force, just noise. That is the normal state. A magnet exists only because that normal state has been violated. When electrons line up, they are not following chaos, they are defying it. They are acting collectively, maintaining a pattern in a universe that constantly tries to erase patterns. That is why magnetism feels mysterious. It is not just a force, it is sustained disobedience. This alignment doesn't happen because electrons are cooperative or intelligent. Forget that idea. Nature does not negotiate. The alignment happens because, under certain conditions, order becomes cheaper than disorder. The system finds a loophole in chaos, and when it does, it locks in. Once enough spins align, they create an environment where staying aligned is easier than breaking formation. The material becomes self-enforcing. The rebellion organizes itself. What began as a fragile pattern becomes stubborn, resistant, difficult to destroy. That's why magnets are hard to erase. You can shake them, drop them, insult them, nothing happens. But heat them, and suddenly the rebellion collapses. Random motion overwhelms alignment. The electrons stop agreeing. The order dissolves. The magnet dies, not violently, quietly, without drama, because chaos doesn't fight, it waits. This is the lesson people miss. Order is always temporary, even in magnets, especially in magnets. And yet, for a time, that order does something astonishing. It reaches beyond itself. It affects other objects. It exerts influence across empty space. A local act of organization creates distant consequences. That should disturb you, because it means the universe allows small pockets of order to punch above their weight. It allows structure to project power. It allows patterns to act like forces. Magnets don't overpower nature, they exploit it. They use the rules of motion, energy, and interaction in a way that looks like defiance but is actually precision. They are not violations of the universe, they are proofs of how subtle the universe is. Break a magnet in half and the order does not disappear, it reorganizes. You don't get a broken rebellion. You get two smaller ones. The pattern survives division. That's not a property of objects, it's a property of systems. And this is where your intuition fails. You want magnetism to be stored somewhere. You want order to be contained. But order is not a substance. It is a relationship between parts. As long as those relationships can reform, the rebellion continues. Magnets teach a brutal truth. Stability is not about strength. It's about cooperation under constraint. The electrons are not strong individually. Together, aligned, they produce something that reshapes behavior at a distance. The universe does not reward force. It rewards coordination. And that is why order is rare. Not because it is impossible, but because it is expensive. It must constantly defend itself against noise, heat, vibration, and time. Most systems surrender quickly. Magnets resist longer than most. So when you hold a magnet, don't admire the force, admire the discipline. Admire the fact that in a universe addicted to disorder, a small piece of matter learned how to stand in formation. Not forever, not perfectly. UT long enough to matter. That is organized rebellion, and it never lasts. Which is exactly why it's worth understanding you. Never create magnetism, you only unlock it. That sentence destroys a comforting illusion. The illusion that humans are inventors of forces. That we manufacture magnetism the way we manufacture machines. We don't. We never did. And we never will. When you make a magnet, nothing new enters the material. No substance arrives. No force is injected. Nothing is added. If that bothers you, good. It means you're paying attention. Every piece of iron already contains everything required to behave like a magnet. The electrons are there, the spins are there, the magnetic effects are there, hidden, neutralized, canceling one another out in silence. Magnetism is present long before you notice it. The only thing missing is permission. Inside ordinary matter, each electron contributes a tiny magnetic influence. On its own, it's insignificant. Even in large numbers, those influences usually point in random directions. Nature does this automatically. Randomness is cheaper. It requires no maintenance. Disorder is the default state. So the material appears non-magnetic. Not because magnetism is absent, but because it is locked. Locked by chaos. When we say we create a magnet, what we actually do is remove the lock. We change the conditions so alignment becomes possible. We expose the system to a strong magnetic field or manufacture it in a way that favors alignment or carefully cool it while imposing order. In every case, we are not creators, we are key holders. The electrons respond not to intention, but to energy economics. Aligning their spins lowers the system's energy under certain conditions. Nature does not ask why. It follows the cheapest path available. Once alignment begins, it becomes contagious. Aligned regions encourage neighboring regions to align. What was once buried becomes self-sustaining. The magnet appears, but nothing appeared. The behavior changed. This distinction matters more than you think, because if magnetism were something you created, you could destroy it completely, erase it, remove it. But you can't. You can only disrupt the order that reveals it. Heat the magnet, and the electrons vibrate violently. Their spins lose discipline. Random motion overwhelms alignment. The magnet vanishes. Where did the magnetism go? Nowhere. It didn't leave. It didn't leak out. It didn't evaporate. The lock closed again. This is why magnets are humbling. They refuse to give you ownership. You can influence them, shape them, use them, but you cannot claim authorship over the force itself. The universe supplied that long before you arrived. Break a magnet in half and watch what happens. You don't get a north without a south. You don't get a dead piece and a live piece. You get two complete magnets. The unlocked pattern simply reestablishes itself locally. That's not manufacturing, that's Revelar. We tend to confuse control with creation. If we can turn something on and off, we assume we made it. But flipping a switch doesn't create electricity. It allows electricity to flow. Magnetism works the same way. And this misunderstanding spreads everywhere. People talk about generating forces, inventing power, creating energy, as if the universe were a warehouse waiting for human approval. It isn't. It's a rule book. You either play by it or nothing happens. Magnets remind you of your actual position. You are not a force maker. You are a condition setter. When the conditions are right, nature reveals its hidden behaviors. When they are wrong, it hides them again. The behaviors were never yours to begin with. This realization should make you more careful, not less impressed. It means the universe is richer than your actions. It means reality contains possibilities that remain dormant until the correct constraints awaken them. Magnetism is one of those possibilities, not created, not owned, not manufactured, unlocked. And once you understand that, you stop asking shallow questions like, how do we make magnets? And start asking the dangerous ones. What else is locked inside matter? What other behaviors are waiting for the right conditions? How much of reality is invisible, not because it's weak, but because it's disciplined into silence? Magnets don't answer those questions. They warn you. They tell you that the world is not built from what you add to it, but from what you allow to align, and that should permanently change. how you think about power. A magnet is proof that invisible rules dominate the visible world. Look at a magnet and you see almost nothing. A dull piece of metal, no motion, no glow, no sign of power. And yet it reaches across empty space and commands other objects to move, not by contact, not by persuasion, by obedience. That alone should make you suspicious of your senses, because everything you think matters. Shape, color, texture, weight is irrelevant here. The magnet doesn't look powerful. It behaves powerful. And behavior always reveals more truth than appearance. What you are witnessing is not a force stored inside an object. You are witnessing the enforcement of rules you cannot see, rules that operate whether you understand them or not, rules that do not announce themselves. The visible world is obedient to an invisible framework inside the magnet. Electrons are in motion. Their spins are aligned, forming an organized pattern. You don't see that, you never will. But that microscopic discipline reshapes macroscopic reality. Paper clips move, compasses turn, motors spin. Entire technologies depend on it. You never touch the rule, you only touch the result. And that's the trap of everyday experience. We believe what we can see, we trust what we can feel, but magnets don't care about your trust. They work anyway. They operate with perfect indifference to human intuition. You can place a magnet near iron and watch attraction happen, but you will never see the cause travel through space. There is no visible rope, no pushing hand, just motion triggered by nothing you can point to. This makes people uncomfortable, so they invent mental shortcuts. They imagine fields as substances, lines in space, something flowing, something tangible. But those pictures are not reality. They are coping mechanisms. A field is not a thing. It is a rule expressed everywhere at once. That rule tells charged particles how to behave if they find themselves in a certain position. It doesn't move objects directly. It defines permission, and matter follows permission without protests. This is why breaking a magnet in half doesn't destroy it. The rule doesn't live in one place. It reasserts itself wherever the conditions allow. Cut the object, and the invisible order simply redraws itself. Two magnets appear because the rules remain intact. Heat the magnet and watch its power fade. Not because the rule vanished, but because disorder disrupted the system's ability to obey it. The law didn't change. The material's compliance did. Distinction matters. The universe does not renegotiate its rules. It does not adapt to your experiments. It does not care if you find it strange. Matter either follows the rules or fails to produce the behavior you expect. Magnets expose this mercilessly. They show you that the real machinery of reality is not made of gears and surfaces, but of constraints and allowances, of interactions defined long before objects exist, of mathematics masquerading as force. And once you see this, you can't unsee it. Gravity works the same way. So does electricity. So does light. Nothing you rely on daily is truly visible. You live inside consequences, not causes. The visible world is the surface foam of deeper structure. This is why understanding magnetism doesn't make the world simpler. It makes it more unsettling. You realize that what you call solid is mostly empty space. That what you call force is instruction. That what you call control is alignment with rules you didn't write. A magnet is small, but it's an honest teacher. It doesn't pretend. It doesn't explain itself. It just works. And in doing so, it tells you something brutal. Reality is not obligated to match your intuition. It operates according to invisible logic, and your senses are merely allowed to observe the aftermath. So the next time you watch a magnet pull iron from a distance, don't ask what the magnet is doing. Ask what rules you are witnessing. Because the visible world is not in charge. It never was. And the magnet is the proof sitting quietly in your hand. Understanding magnetism humbles intelligence. Not because it is complicated, but because it refuses to flatter you. At first glance, magnetism looks simple. Opposites attract, like poles repel. Draw a few lines, memorize a few rules, solve a few problems, and you feel clever. That confidence is a trap. Magnetism lets you feel smart just long enough to expose how shallow your understanding really is. You can describe what happens with precision. You can predict outcomes with equations. You can build machines that rely on it. And still, you don't know why reality behaves this way instead of some other way. That gap is where intelligence gets humbled. When you study magnetism seriously, the first thing you learn is not power, it's limitation. You realize that the words you use are placeholders. Field, force, interaction. These are not explanations. They are labels pinned onto behavior. you cannot directly observe. You never see magnetism. You never touch it. You never isolate it. You only see matter responding to invisible rules. That should unsettle anyone who believes intelligence is about mastery, because magnetism does not submit to understanding the way mechanical systems do. You can open a clock and see how it works. You can't open a magnet and point to the place where magnetism lives. There is no such place. Inside the magnet are electrons, spins, alignments, and even there, certainty dissolves. Try to explain why electron spin exists at all, and language collapses. It is not rotation. It is not motion in space. It is an intrinsic property with no classical picture. Already, intuition has failed. Then you learn something worse. Magnetism is not even a standalone phenomenon. It is inseparable from electricity. Two faces of a deeper structure. Change your frame of reference and one becomes the other. What looked like a magnetic effect was electric all along, or vice versa. Your neat categories fall apart. And if you keep going, magnetism stops being about magnets entirely. It becomes about symmetry, conservation laws, and abstract mathematical relationships that do not resemble the physical world at all. The equations work flawlessly, while your understanding lags behind, dragging metaphors that no longer apply. This is where intelligence meets its boundary, because intelligence loves explanation that feels complete. Magnetism offers none. It offers accuracy without comfort. It allows prediction without comprehension. You can calculate the field around a wire without knowing what a field is. You can design a motor without knowing why nature honors these equations. You can pass exams without ever touching the core mystery. Magnetism lets you succeed while remaining ignorant, and that is its quiet cruelty. The deeper you go, the clearer it becomes that understanding magnetism does not elevate you above nature. It pushes you lower. It forces you to admit that reality is not constructed from common sense, but from structures that tolerate no mental shortcuts, every attempt to visualize. Magnetism eventually breaks. Field lines are not real. They don't exist in space. They are bookkeeping tools, helpful lies, and yet without those lies, we are lost. So intelligence adapts. It becomes humbler. It learns to operate without pictures. It accepts that explanation can be operational rather than intuitive, that knowing how to calculate is not the same as knowing what is happening. Magnets don't care if you understand them. They don't reward insight. They obey the rules regardless. And that is the final insult to ego, because intelligence wants to be central. Magnetism proves it is peripheral. The universe does not wait for your comprehension. It behaves first. You explain later, poorly, approximately, and always incomplete. So when someone claims they understand magnetism, what they usually mean is that they can work with it. That's not the same thing. The real understanding is realizing how much remains opaque. Magnetism teaches restraint. It teaches you that intelligence is not dominance over nature. It is negotiation with mystery, that the smartest position is not certainty, but respect for the depth of what you cannot reduce. And once you accept that, something important happens. You stop demanding that reality makes sense to you. You start learning how to listen.
Space might be finite, immeasurable, volume, but it has no edge, no end in. The way you're imagining it. Imagine a bug, a tiny flat bug living on the surface of a ball. This bug can only perceive two dimensions. It can move forward, backward, left, right, but it has no concept of up or down for this. Bug, the surface of the ball is the entire universe. There's nothing else. Now, does this bug's universe have an edge? No. The bug can walk in any direction forever and it will never hit a wall, never fall off, never reach a sign that says end of space. But wait, is the bug's universe infinite? Also, no. The surface of a ball has a definite size. It's measurable. It's finite. So, how can something be finite but have no edge? Here's the secret. The surface curves. It wraps around. If the bug walks in a straight line long enough, it ends up exactly where it started without ever turning around. The bug circumnavigates its entire universe just by going straight. Finite but unbounded, limited size, but no boundary. That's the key. Now, here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it, without ever floating up into the third dimension and looking down at the ball. The bug can figure it out from within. How? by doing geometry, by measuring things carefully. Now, here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it, without ever floating up into the third dimension, and looking down at the ball, the bug can figure it out from within. How? By doing geometry, by measuring things carefully. Let me show you what I mean. On a flat surface, if you draw a triangle and measure all three angles, they always add up to exactly 180. Always, every triangle, no exceptions. But on a curved surface like a sphere, the angles add up to more than 180. The triangle is fatter than it should be. On a flat surface, if you draw a circle and measure the circumference, it's always a little more than 6 times the radius. That's just how circles work. But on a sphere, the circumference is less than you'd expect. The surface curves, so the circle pinches. The bug can do these measurements. The bug can discover through careful geometry that something is wrong with its space, that the rules don't work the way they should. That space itself is curved. And here's the beautiful part. The bug does this without ever leaving its universe, without ever seeing it from the outside. The curvature is intrinsic. It's built into the fabric of space itself. Our universe might be exactly like that. We might be the bugs. Einstein told us that. Space is curved, not metaphorically, not as a mathematical trick, actually. Physically curved. The fabric of space, the void between stars, the emptiness. You're sitting in right now, it bends. And what causes the bending? Mass, matter, energy. Every star curves space. Every planet curves space. Even you curve space just a tiny bit. The more mass of something is, the more it warps the space around it. So here's the picture. Our three-dimensional space might curve in a fourth dimension that we can't perceive directly, just like the bug's two-dimensional surface curves. In the third dimension, we can't see the curvature by looking at it, but we can detect it, we can measure it, and if our space curves enough, if it curves all the way around, then it closes on itself like the surface of a sphere. But in 3 dimensions, what would that mean? It would mean the universe is finite, it has a definite size, a measurable volume, but it would also mean the universe has no edge, no boundary, no wall. If you got in a spaceship and flew in a perfectly straight line, just kept going and going, for billions of years you wouldn't hit a wall, you wouldn't fall off an edge, you wouldn't reach the end, you'd end up back where you started. Here's the truth. The universe might be finite, but unbounded, limited, but edgeless. It might have a size, but no border. And this answers the question everyone asks, the question that keeps people up at night. What's outside the universe? Nothing. Not empty space, not darkness, not some other realm, nothing. Because outside doesn't exist. Think about it. What's outside the bug's universe? What's outside the surface of the sphere? From the bug's perspective, the question makes no sense. The surface is everything. There is no outside. For us, it might be the same. Space-time is everything. There is no outside. The question assumes something that doesn't exist. And now comes the shock. This isn't just philosophy. This isn't just speculation. We can test it. We are testing it. Remember how the bug could detect curvature by measuring triangles and circles. We can do the same thing on a cosmic scale. We can look at the largest structures in the universe. We can measure the angles of giant triangles formed by distant galaxies. We can check if the geometry works out the way it should for flat space. And what do we find? So far, the universe looks very close to flat on large scales. Very close. But very close doesn't mean exactly flat. There could be a tiny curvature that we haven't detected yet, a slight curve that would only show up at scales larger than we can currently measure. If the universe is positively curved like a sphere, then it's finite and closed. You travel far enough, you come back home. If the universe is negatively curved like a saddle, then it's infinite and open. It goes on forever in every direction. If the universe is perfectly flat, then it's also infinite. Space just keeps going with no end. But here's what we know for certain. Whether the universe is finite or infinite, it doesn't have an edge. It doesn't have a wall. There's no boundary. You can reach where space just stops. Either it goes on forever or it wraps around on itself. Those are the options. Edge of the universe isn't one of them. Let me say that again because it's important. Space doesn't end either. It's infinite and keeps going, or it's finite and loops back. But there's no wall, no border, no end in the way your brain wants there to be. The universe is not a room. It's not a box. It's not. Contained inside something larger. The universe is everything and outside is, not a place that outside might not exist. You might be wondering, okay, space is curved, but curved into what? If the bug surface is curved in. Three-dimensional space, then our three-dimensional space must be curved. In what? A fourth dimension. And here's where we have to be careful. We don't need a higher dimension for space to be curved. The curvature is intrinsic. It's a property of space itself, measurable from within without reference to anything outside. Let me explain what I mean. When we say the bug's universe is curved, we're describing it from the outside. We see the ball. We see the surface wrapping around. But the bug doesn't see any of that. The bug just notices that geometry doesn't work. Right? Triangles are weird. Circles are weird. Something is off. The bug discovers curvature through measurement, not through seeing a higher dimension. We're in the same situation. We can measure the curvature of our space without needing to see it from a fourth dimension. We just do geometry on large scales and check if the results match, flat geometry or not. Here's the key. Curvature is not about bending into something. Curvature is about geometry, being different than expected. That's the definition. A curved space is a space where the rules of flat geometry don't apply. So stop trying to visualize the universe as a balloon floating in some larger space. That image is misleading. There's no larger space. There's just our space with its own intrinsic geometry, which might be curved. Now, let's talk about something else, because curvature isn't the only strange thing about space. Einstein told us something even more remarkable. Space and time are connected. They're woven together into a single fabric called space-time. And when we talk about the curvature of the universe, we're really talking about the curvature of space-time. This matters because it changes everything. Here's an example. You probably know that time passes at different rates depending on where you are. A clock on a mountain runs slightly faster than a clock in a valley. A clock on a speeding airplane runs slightly slower than a clock on the ground. These aren't mechanical errors. These aren't problems with the clocks. Time itself runs at different rates in different places. And why? Because of curvature. Mass curves space-time. And when space-time is curved, time flows differently in different locations. Think about what this means. Near a massive object like the Earth, space-time is curved. And that curvature affects not just space, but time. Clocks tick. Slower near massive objects. Time literally passes more slowly. This has been measured. This is not speculation. Scientists have taken identical atomic clocks, put one on a plane and one on the ground, flown the plane around, and compared the clocks afterward. They're different by tiny amounts, but measurably different. The clock on the plane experienced slightly less time than the clock on the ground because it was higher up, further from Earth's mass, in a region where space-time is less curved. But wait, there's more. This curvature of space-time isn't just an interesting fact, it's the explanation for gravity. You were probably taught that gravity is a force, that the Earth pulls on you, that there's some invisible rope connecting you to the planet, yanking you downward. But that's not what's happening. Here's the truth. You're not being pulled down. You're following the natural path through curved space-time. Let me try to make this intuitive. Imagine you're in a spaceship, far from any planet or star, no gravity, you're floating. Now the spaceship starts accelerating, it fires its engines and speeds up. What happens to you? You get pressed against the back of the ship. You feel weight, you feel exactly like you would if you were standing on a planet. Einstein realized something profound. There's no way to tell the difference If you're in a closed box and you feel weight, you cannot determine whether you're on a planet being pulled by gravity or in a spaceship that's accelerating. The experiences are identical. This is called the principle of equivalence. And it's the foundation of everything. Here's why it matters. If acceleration and gravity feel the same, then maybe they are the same. Maybe gravity isn't a force at all. Maybe what we call gravity is actually the effect of curve. Space-ame. Think about it this way. When you drop a ball, it falls, you think gravity is pulling it down, but actually the ball is just following a straight line through curved space-ame. That sounds crazy, right? How can falling be a straight line? Because in curved space-ame, straight lines look curved from our perspective. The ball is taking the most natural path through. Space-ame, the shortest path, the path that any free object would follow. We call these paths geodesics. And in flat space-time, geodesics are straight lines, but in curved space-ame, geodesics look curved to us. They look like orbits, like falling, like the motion we associate with gravity. So the Earth isn't pulling you down. The Earth is curving the space-ame around it. And you, by existing in that curved space-ame, naturally move toward the Earth, not because of a force, but because of geometry. Now watch this. This explains something that puzzled scientists for centuries. Why do all objects fall at the same rate? A feather and a hammer in. A vacuum hit the ground at the same time. Why? If gravity were a force, you'd expect heavier objects to experience more pull, but they also have more inertia, more resistance to acceleration. And these two effects exactly cancel. It seems like a coincidence, but in the curved space-time picture, it's not a coincidence at all. Objects aren't being pulled. They're following geodesics. And the geodesic doesn't care what the object is made of. A feather and a hammer follow the same curved path through space-ame because the path is determined by the geometry, not by the object. Here's the secret. Gravity is not a force. Gravity is geometry. The curvature of space-time is what we experience as gravity. And this brings us back to the question of the universe. If mass curves space-time and the universe is full of mass, then the universe is full of curvature. Every star, every galaxy, every particle of matter contributes to the overall curvature of space-time. The total amount of matter and energy in the universe determines its overall shape, its geometry, whether it's curved like a sphere or curved like a saddle or perfectly flat. And that geometry determines the fate of the universe. If there's enough mass, space curves. Positively, the universe is closed. It's finite. And if you wait long enough, it might even collapse back on itself. A big crunch. If there's not enough mass, space curves negatively. The universe is open. It's infinite. It expands forever, getting colder and emptier. If there's exactly the right amount of mass, space is flat. The universe is infinite. It expands forever, but just barely right, on the edge between collapse and eternal expansion. Which one is our universe? We've measured it. We've looked at the cosmic background, radiation, the leftover glow from the Big Bang. We've studied the distribution of galaxies. We've calculated the total mass and energy. And the answer is our universe is very close to flat, remarkably close. So close that it's almost suspicious, but very close to. Flat leaves room for mystery. There could be a tiny curvature we haven't detected. And even if it is perfectly flat, the question remains, why? Why? This particular geometry and not some other? Here's what we know for sure. Space is curved. Mass causes curvature. The geometry of the universe depends on what's in it. And that geometry determines whether the universe is finite or infinite, whether it has a shape that closes on itself or extends forever. The universe is not a fixed stage where things happen. The universe is a dynamic fabric that bends and warps and shapes itself according to its contents. And we're part of that fabric. We curve it, and it curves us. So let's bring this all together because we've covered a lot of ground, and I want to make sure the picture is clear. Space is curved. The universe might be finite, but without edges. There's no outside. Gravity isn't a force, but geometry. Mass tells space and how to curve, and curved space-time tells mass how to move. But there's one more thing we need to talk about, and it's the hardest part of all. Our intuition is wrong, completely, fundamentally, hopelessly wrong about all of this. And that's okay. Here's why. Your brain struggles with these ideas. You evolved on a small planet, moving at slow speeds, experiencing weak gravity your ancestors needed to throw spears at. Animals find ripe fruit, avoid predators they did not need to. Understand the curvature of space and me. So your brain built a model of reality that works for everyday life. A model where space is flat, where time flows at the same rate everywhere, where things fall because they're pulled by invisible forces, where everything is contained inside something larger. That model is wrong, but it works well enough for surviving on Earth. So evolution kept it. The problem comes when you try to. Think about the cosmos. You try to. Imagine the shape of the universe when you ask questions like, what's outside? Your brain uses its everyday model and gets nonsense answers. Here's the truth. The universe is not required to make sense to your intuition. The universe is required to be consistent with itself. And it is. The mathematics works. The predictions match. Observations. The theory holds together. It just doesn't feel right. And that's your problem, not the universe's problem. Now, let me address something that might be bothering you. If the universe could be finite and without edges, if it curves back on itself, what does that actually mean for us? What difference does it make? Well, here's one way to think about it. Imagine you're an astronaut. You get in the most advanced spaceship ever built. You pick a direction and you start flying perfectly straight, no turns, just forward forever. In an infinite universe, you fly forever and never return. Every moment takes you somewhere new. Space goes on without end. But in a finite curved universe, something strange happens. After billions of years of travel, the stars start to look familiar. The galaxies seem like ones you've passed before, and eventually you arrive back at Earth, right where you started. You circumnavigated the universe without ever turning around, just by going straight. That's what it means for space to be curved and closed. Straight lines become loops. Forward forever becomes back to the beginning. Now, practically speaking, this doesn't matter much for our daily lives. The universe is so large that even if it's finite, it's far too big for us to ever circum. We'll never build a ship fast enough or live long enough to complete the journey. But conceptually, it changes everything. It means the universe doesn't need an outside. It doesn't need a container. It doesn't need edges or walls or boundaries. It can be complete in itself, self-contained, everything that exists, existing within a structure that loops back and closes. Here's the key. The question, what's outside the universe, assumes a certain kind of universe. It assumes space is like a room contained inside something larger. But if space curves back on itself, that assumption is wrong. There is no outside. The question dissolves. It's not that we don't know the answer. It's that the question doesn't apply. You know what? People hate this answer. They really do. They want there to be an outside. They want there to be something more, something beyond. Their brains crave it. But the universe doesn't owe us satisfaction. The universe is what it is. And part of understanding physics is accepting that some questions are based on false premises. What's outside the universe might be one of those questions. Not a mystery we haven't solved yet, but a question that was never valid to begin with. Now watch this. There's something beautiful about this picture, something I don't want you to miss. We are tiny, unimaginably small compared to the cosmos. We live on a speck of dust orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies. And yet we figured this out. We, the bugs on the surface, discovered that our space is curved, We measured the geometry. We tested the predictions. We built a theory that explains gravity as curvature and describes the shape of the universe itself. We can't see the curvature directly. We can't float up into a higher dimension and look down, but we deduced it through mathematics, through careful measurement, through the power of human thought. That's remarkable. It's genuinely miraculous that creatures made of atoms can understand the fabric of spacing. That we can ask, what is the shape of everything, and actually make progress toward an answer. Let me leave you with something to think about. We don't know for certain if the universe is finite or infinite. We don't know if it curves back on itself or extends forever. The measurements are close to flat, but close isn't certain. What we do know is that the universe is far stranger than our intuition suggests. The space bends, time stretches, geometry depends on. What's in it? The cosmos might be a closed loop with no outside, or an infinite expanse with no end, either way. There's no wall, no edge, no boundary where space stops and something else begins. The universe is infinite with an end, or finite without edges, or infinite without edges, but never, never a box with walls. Here's the deepest part. When you look up at the night sky, you're not looking at objects scattered inside a giant room. You're looking at matter embedded in curved space-time. Every star, every galaxy is part of the fabric, and the fabric shapes itself around its contents. The universe isn't a container holding things. The universe is the things and the space between them, woven together, curving and flowing and existing as one unified structure. There is no outside, because there is nothing but the universe. It is complete. It is whole. It is everything. I know this is hard to accept. I know your brain wants more, wants an answer that fits into familiar categories, wants to know what's beyond, but sometimes the deepest understanding comes from accepting that certain questions don't have the kind of answers we expect. That reality is structured differently than we imagined. That the universe is under no obligation to make intuitive sense. So what's outside the universe? Nothing. Not empty. Space, not darkness, not another. Universe. Nothing, because outside is not a concept that applies. The universe might be finite, it might be infinite, but either way, it's everything, and everything doesn't have an outside. That's not a failure of knowledge. That's a feature of reality. That's how the cosmos actually is. And we figured that out. Tiny creatures on a tiny planet looking up at the stars, doing geometry, testing predictions, pushing the boundaries of understanding.
If you wanted to learn all fundamental particle physics, you would first need to know that the world we live in is governed by four forces: the strong, weak, electromagnetic, and gravitational force. We have a quantum description for three of these forces. The odd one out is gravity, for which there is no quantum theory as yet, but it is so weak that it doesn't have a significant effect at the quantum level, since the other forces overpower it. So it is generally ignored in quantum calculations, but after almost 100 years of scientific progress, we can very accurately describe the other three forces in terms of quantum field theories. These theories explain how particles like quarks and electrons interact with each other via these three forces. Each force is mediated by a force carrier, also called a mediator. The electromagnetic force is mediated by the photon, the weak force by the W and Z bosons, and the strong force by gluons. In a quantum field theory, we represent each of these mediator particles with a field. For example, the photon field mediates the electromagnetic force between electrically charged particles like electrons. Other fundamental particles of the Standard Model are also represented by their own respective fields. And these fields can interact with each other. Thus, the photon field can interact with the electron field, causing a repulsion of two electrons, for example. If we generalize this concept of force-carrying particles interacting with other particles, we can get all fundamental particle physics. We could take space-time, add a quantum field for each type of fermion, like quarks, add quantum fields for the appropriate bosons, like gluons, that mediate the force that the quark is subject to, and we can get a great representation of how it all works. These theories can be complicated, but American physicists Richard Feynman came up with an ingenious way to represent these interactions in what is now called Feynman diagrams. And even though these diagrams represent complicated mathematical equations, they can be visualized intuitively and drawn for any process using some simple rules. If you want to understand all fundamental particle physics with the help of these simple intuitive Feynman diagrams, then Merry Christmas, because that's coming up right now. Before we review all particle physics, I'd like to take a moment to thank special offer, Magellan TV, for making this episode possible. Magellan is an ad-free documentary streaming service created by the filmmakers themselves. The documentary collections are richer and broader than about any other streaming service. You can dive deep into subjects like history, culture, science, and technology, and see many of them in 4K. I'm excited to tell you that Magellan is now offering a buy one, get one free gift card for the people in your life you want to give the gift of knowledge. If you're new, you'll get a free 1-month trial of Magellan. If you're already a member, you'll get an extra month anytime you purchase a gift card. There has never been a better time to spread the gift of knowledge. I highly recommend Magellan TV, so be sure to click the link in the description. First, let's learn to make a simple Feynman diagram. To do this, we'll start with particles, charges, forces, the standard model, which is like the periodic table for fundamental particles. What is important here is to understand what the different classes of particles can do. So on the left, the 12 fermions are represented with straight lines with arrows in Feynman diagrams. The arrow is important, just like how in an electrical circuit, the current flows through the circuit. The arrows represent the flow of fermions. No two arrows point towards each other. This is to conserve the fermion current, or in other words, we must have the same number of fermions in the end as we started with. Note, there are some other notations which use these arrows differently. If we consider time in the x direction, then we can interpret fermion arrows going forwards in time as matter particles and fermion arrows going backwards as antimatter particles. This is the general rule for all fermions. Now, the fermions can be divided up further in terms of charges. When I say charges, I mean the electric and color charge. If you don't know what a color charge is, please check out my previous video on QCD. All 6 quarks have color charges. All particles with color charges interact with the strong nuclear force. Thus, all quarks feel this force. The quarks also have an electric charge, so they also feel the electromagnetic force. The other class of fermions are the leptons. These can be divided into the electron, which makes up an atom, and its heavier cousins, the muon and tau particles. These all have electric charges but no color charges, so they feel the electromagnetic force but not the strong force. The last 3 leptons are the neutrinos. These do not have a color charge or an electric charge. Thus, they are not affected by the strong or electromagnetic forces, and they have very low mass, so only slightly affected by gravity. This is what makes them very difficult to detect. You might ask, hey, what about the weak force and its charge? The answer is that all fermions carry something called weak isospin. This can be thought of as as the charge of the weak force. For fermions, it can be +1/2 or -1/2. So all fermions interact with the weak force. But weak isospin can also be -1, 0, and +1. The boson has a weak isospin of -1. WPLS has +1. Higgs has 1/2. And Z boson and photons have a weak isospin of 0. Note that this Z arrow is not the same as having no isospin. Both the Z and photon interact with the weak force. Everything in the standard model has a weak isospin except gluons. So gluons do not interact with the weak force. Weak isospin is a quantum number relating to the weak force. It is a property just like electrical charge is a property of some particles. The number of the charge is just related to how they feel it. Weak isospin must also be conserved. Just like you must conserve electric charge and color charge, it is a stretch to call the weak force a force. It's more like a power. The weak force has the power to turn one particle into another particle. So, for example, it can turn a down quark into an up quark, turning a neutron into a proton by emitting a W- boson. It is the only force that can do that. Electromagnetism and the strong force can't do this. To recap, quarks interact with all forces. Electron-like particles interact with electromagnetism and the weak force, but do not interact with the strong force. Neutrinos only interact with the weak force and nothing else. Only quarks and gluons carry the strong force. Higgs bosons do not interact with photons or gluons. They confer mass to fundamental particles. So all fundamental particles with mass interact with Higgs. With that, you have the basics needed to understand Feynman diagrams. There are potentially a large number of diagrams, but we can build almost everything by looking at the most important ones where fermions interact with forces. The simplest force is electromagnetic force, described by QED, which, as we know, interacts electromagnetism with quarks and leptons. Note that the W bosons, which are the mediator particles for the weak force, are charged, so they also feel this force, but we'll ignore them for the moment. Let's interpret one of the simplest diagrams shown here. The x-axis represents time. An arrow pointing to the right represents matter particles. There are two ways this diagram can be interpreted. We can view it as an electron moving from left to right, while at the same time a photon moves from bottom to top. This would depict a photon being absorbed by an electron. This is how the electron in an atom can move from a lower orbit to a higher orbit by absorbing the energy from the photon. We can also view this as an electron moving from left to right, emitting a photon, and then continuing. In this scenario, it would represent the electron losing energy by emitting a photon. This is how an electron in an atom moves from a higher orbit to a lower orbit. By the way, this is also how a laser works. How is electromagnetic repulsion depicted in Feynman diagrams? As we discussed, the force-carrying particle for electromagnetism is the photon. This diagram, also called Muller scattering, depicts repulsion. Two electrons come near each other. An exchange of virtual photons causes a transfer of momentum, which pushes the two electrons apart. Note that we cannot measure the virtual photons, only the incoming and outgoing electrons. So sometimes this diagram is drawn like this. These both depict the same process. What about electromagnetic attraction? The diagram for this, called Baber scattering diagrams. There are two potential diagrams. The first diagram depicts an electron and positron that have opposite charges attracting each other. This also happens through the exchange of virtual photons. This looks very similar to the diagram for repulsion. The only difference is that the photon exchange in this case results in exchange of negative momentum, which attracts two particles instead of positive momentum, which repels two particles. We can see this in our boat analogy, where the boats represent electrons and the object being thrown is like the virtual photon. Positive momentum exchange is like the two people throwing basketballs at each other, which pushes the boats apart. But a negative momentum exchange is like two people throwing boomerangs, which results in the boats being attracted to each other. The second diagram shows a different phenomenon, which can also occur when electrons and positrons are near each other. This shows that when the anti-particle pair come near each other, they annihilate, resulting in energy production or photons being created. The energy of these photons, in turn, can create a new electron-positron pair. Weak force. This leads us on to the slightly more complicated weak force. This force is felt by all of the standard model particles except gluons. The most interesting weak force diagrams involve W bosons, which can have a +1 or -1 electric charge. These particles can do something very special. They can change the identity or flavor of the particle. For example, they can change an up quark into a down quark. This is so important that we probably would not exist without it. So, for example, here's one of the most important weak force interactions relevant to life. This involves a neutron decaying into a combination of a proton, electron, and antineutrino. On the left side, we have a neutron, which is composed of one up quark and two down quarks. One of the down quarks can change flavor and become an up quark. This happens due to the weak force mediator particle. When a boson emitted, the down quark changes its flavor to an up quark. This boson then almost immediately decays into an electron, an antineutrino. Because the new particle now has two up quarks and one down quark, our original neutron is turned into a proton. Note that charge is still conserved because the emitted negative charge of the electron is balanced by the positive charge of the proton, and weak isospin is also conserved because the isospin change of +1 created when a down quark changed to an up quark is balanced by the combined -1 spin of the electron and antineutrino. If this decay did not occur, the early universe may have been awash with neutrons and atoms may never have formed. Another interesting weak force interaction involves the Z boson. It has no electric charge, just like the photon. But unlike the photon, it can mediate interactions with electrically neutral particles like the neutrino and the Higgs. So, for example, as the Feynman diagram shows, a Z boson can transfer spin or momentum between an electron and a neutrino. But in the process of doing so, it does not transfer any charge and leaves the particles otherwise unaffected. Strong force. This brings us to strong force, which is the most complicated mathematically, but since it only relates to quarks and gluons, there are fewer interactions to understand. One of the simplest diagrams is the interaction diagram. Here, a pair of quarks simply change color. This process happens all the time inside protons and neutrons, and this color charge exchange is the glue that binds the quarks together and keeps them confined to the inside of nucleons. A blue and red quark, for example, can change colors via the exchange of a gluon. So, on this diagram, we have a red quark coming from the top left. It emits a gluon with a combination red and anti-blue color charge. Gluons always have a combination of color anti-color charges. The outgoing anti-blue of the gluon immediately turns the quark into a blue quark. The blue quark at the bottom absorbs this gluon. Its blue color gets neutralized by the anti-blue contained in the gluon. And this quark turns red by absorbing the red that was also part of the gluon. Note that color is conserved in this interaction. Because gluons themselves contain color charges, they also interact with each other via complicated diagrams. These gluon-gluon interactions is what the flux tubes inside nucleons are made of. These tubes are formed when you try to pull quarks apart. As discussed in the video about QCD, the diagrams here show possible constructions. Now, let's look at what is the most complicated Feynman diagram in this video, but may very well also be the most important. This diagram represents the strong force interaction that binds protons and neutrons together in the nucleus. Without this interaction, there would be no atoms heavier than hydrogen, and life as we know it would not exist. Essentially, this diagram shows that a proton and neutron interact with each other via gluons, yielding some residual energy which becomes mesons. These mesons are a combination of quark, anti-quark pairs. These, in turn, mediate the strong force between the proton and neutron. Let's take a close look at exactly how this attractive force works. We have a proton up top and a neutron at the bottom. Keep in mind that color must always be conserved. That is, the three quarks inside proton or neutron must be a combinati of red, blue, and green, which combine to make a neutral white color. Let me clarify that this is the same way that optical colors combine, but color charge is a metaphor and has nothing to do with colors that you can see with your eyes. Inside the proton, the blue up quark interacts with the red down quark via a gluon. This turns the up quark red and the down quark blue. As this down quark leaves the proton, an anti-blue anti-quark is created together with a green down quark via a gluon interaction between the green up quark, which was initially green but turns blue. The blue down quark and anti-blue anti-down quark leaves the proton forming a color charge and charge neutral pi meson. The newly created green down quark remains in the proton. The pi meson now interacts with the neutron. The anti-down quark of the meson annihilates the down quark of the neutron. At the same time, there is a color exchange between the red down, blue down, and anti-blue anti-quark, such that the quark which is not annihilated becomes red. The down quark of the meson joins the neutron by taking the place of the annihilated down quark. At the same time, an exchange of colors occurs with the green up quark of the neutron such that the up quark turns blue and the new down quark from the pi meson turns green. You might ask, why are so many color exchanges happening in this interaction? The color exchanges have to happen in order to maintain a neutral charge in both the proton and neutron. That's the way quantum chromodynamics works. It can't work without it. Note that this interaction works equally well both ways, whether you go up or down. Also note that these virtual meson interactions are what keep protons and neutrons bound together in atoms. But the attraction is much weaker than the gluon interactions that keep quarks within the nucleons, and they work only at very short distances, much smaller than the width of the proton. The last thing I want to show is how physicists produce the long sought-after Higgs boson. While there are several ways it can be made, the most prominent process used at the Large Hadron Collider is the so-called gluon fusion process. What happens is that in some high-energy proton-proton collisions at the LHC, two high-energy gluons can be produced. These can, in some cases due to strong force interactions, turn into top quarks and fused together via a triangle loop. This loop represents top quark, anti-top quark creation and annihilation. The energy of this annihilation can create a Higgs boson. Because the top quark has the highest mass of all elementary particles, it has the best chance to decay into a Higgs boson, which has the second highest mass of all the elementary particles. In general, when particles decay, they tend to decay into the next highest mass particle, even though there are an endless number of Feynman diagrams, if you understand. The ones I just talked about, and you understand the most important diagrams responsible for the physics of our everyday lives, ignoring gravity. My message to you is that even the most...
This is what most schools are creating. A hold up the wind up robot, wind it up. Let it walk in circles, I wind it up. It follows its programming. Does exactly what it's told. Repeats the same pattern over and over. No deviation, no creativity, no thinking. A memorization machine. Put down the robot, pick up the blocks. This is what we should be creating. Hey, start building something with the block C open-ended, creative. Problem solving. Experimenting. Trying. Failing, adjusting, building something that didn't exist before. A thinker? Hey, put down the blocks, look at audience A. Right now, our education system is mass producing the robot. Children who can recite facts, who can follow procedures, who can pass standardized tests, who can do exactly what they're told. But can they think? Can they solve new problems? Can they create? Can they adapt when the situation isn't what they've been programmed for? Add a pause, most of them can't. Because they've been trained to memorize, not to think. They've been turned into machines, not developed as thinkers, of direct addressix. And if you're a parent, a teacher, or anyone who cares about the next generation, this should terrify you. Because the world doesn't need more memorization machines. We have actual machines for that. Computers that can store and retrieve information far better than any human. What the world needs, what your children need, is the ability to think, to reason, to solve problems that don't have predetermined answers, to create solutions that don't exist yet. Richard Feynman understood this deeply. He saw what the education system was doing to children, and he fought against it. He showed us how to raise thinkers instead of memorization machines. Today, I'm going to show you what he discovered. I'm going to show you what's broken and how we're educating children. And I'm going to show you how to fix it, how to raise thinkers. Real thinkers. Children who can actually use their minds instead of just storing information in them. Hey, walk across stage. Let me start with a story. This story changed how Feynman thought about education forever. And once you hear it, it'll change how you think about it too. It's the 1950s. Feynman's father takes him for walks in the woods. Young Richard, maybe 6, 7 years old, and his father teaches him about nature, but not the way other parents teach. Not by telling him facts. Not by making him memorize the names of birds and plants. Far share the method. Here's what Feynman's father does. They see a bird. And his father says, see that bird. Do you know what kind of bird that is? And young Richard says, no. And his father says, it's a brown-throated thrush. But in Germany they call it a Hausenfugel. And in Chinese they call it a chungling. And in Japanese a Katano-tekta. Ice pause. No. His father says, you know what that bird is called in 4 different languages. But you still know absolutely nothing about the bird. You only know what different people call it. Continue the story. Then his father says, now let's look at what the bird actually does. See how it pecks at its feathers. Why do you think it does that? And they observe, they hypothesize, they think about it. Not memorizing names. Understanding behavior, thinking about why. Make the point, that's the difference. That's the entire difference between raising a thinker and creating a memorization machine. The memorization machine knows the bird is called a brown-throated thrush. That's what you're supposed to know for the test. That's what gets you the points. The thinker understands why the bird behaves the way it does, observes, questions, reasons, develops actual understanding of actual reality. A jumper get intensa, and here's what Feynman realized: most schools are teaching kids to memorize the names. This is a brown-throated thrush. This is mitochondria. This is the Pythagorean theorem. This is the capital of France. Names, labels, facts, information to be stored and retrieved. But they're not teaching kids to think about the bird, to understand mitochondria, to reason about why the Pythagorean theorem is true, to think about why Paris became France's capital, or direct statement, they're creating memorization machines, not thinkers. And those memorization machines are completely unprepared for real life, because real life doesn't ask you to recite facts. Real life presents you with novel problems that require actual thinking. Present the core issue. So let me show you exactly what's wrong. The specific ways our education system creates memorization machines instead of thinkers. Because once you see these, you can't unsee them, and you can start doing something different with your own children. And first problem 1, we reward correct answers instead of good thinking. A child solves a math problem, gets the right answer, gets a gold star, gets an A, gets praise. Another child solves a math problem, gets the wrong answer, but shows creative thinking, tries a novel approach, demonstrates genuine reasoning even though it doesn't work, gets an F, gets correction, gets disappointment. Pause. What does this teach children? It teaches them what matters is the correct answer. How you think doesn't matter. The process doesn't matter. Only the result matters, so facts make the impact clear. So children learn to find the shortest path to the correct answer. Memorize the procedure. Follow the steps. Don't think creatively. Don't try novel approaches. Don't risk being wrong. Just produce the correct answer. That's what gets rewarded. If Falzer share Feynman example of Feynman told a story about this. He's talking to a child who's been taught that energy is something that makes things go. So Feynman asks, does a coiled spring have energy? And the child confidently says no, because it's not moving. The child has memorized that energy makes things go. So if something isn't going, it doesn't have energy. That's the logic. Ayers make the point, the child got the answer wrong. But was the child stupid? No. The child was thinking logically from what they'd been taught. The problem wasn't the child. The problem was the teaching. Teaching a definition without teaching understanding. Teaching words without teaching concepts. Creating a memorization machine instead of a thinker. Second problem, problem 2, we punish mistakes instead of treating them as learning. A child doesn't know something, admits it, says I don't know, gets marked wrong, feels shame, learns not knowing is bad. A child tries to solve a problem, makes a mistake, gets it wrong, gets corrected, gets a bad grade, learns making mistakes is bad. I get passionate, this is devastating. This is how you kill thinking, because thinking requires not knowing. Thinking requires making mistakes. Thinking requires being wrong on the path to being right. But we punish all of that. We punish admission of ignorance. We punish errors. We punish the entire thinking process. Let's make the contrast. Thinkers aren't afraid of being wrong. Thinkers expect to be wrong initially. That's how thinking works. You start with an idea, you test it, it's wrong, you adjust. You try again. You're wrong differently, you adjust again. Eventually you're right. But memorization machines are terrified of being wrong because they've been trained that wrong is bad. Wrong is failure. Wrong is shameful. Share what this creates. So they don't think, they wait to be told the right answer. They memorize it, they repeat it, safe. No risk of being wrong, no thinking required. Share Feynman's approach, or Feynman loved being wrong. When someone proved him wrong, he'd get excited. Oh, I was thinking about this incorrectly. Now I can think about it better. Thank you for showing me where my thinking was flawed. A being wrong meant learning, meant improving, meant thinking was happening. Make the point that that's a thinker. Someone who sees mistakes as progress, as information, as necessary steps toward understanding. But our education system teaches the opposite. Teaches kids to avoid being wrong at all costs. Teaches them to stop thinking and start memorizing. Third problem, problem 3, we teach what to think instead of how to think. A child asks C, why is the sky blue? Most teachers say, because of Rayleigh scattering. The atmosphere scatters shorter wavelengths more than longer wavelengths. So blue light scatters more. The child memorizes this, repeats it on the test, gets an A. But does the child understand? Can the child reason about it? If you asked, why isn't the sky violet then? Could the child figure it out? No, because they memorized what to think. They weren't taught how to think about it. Acts show the alternative of Feynman's approach. Why do you think the sky is blue? What could cause that? Let's think about what we know. Light from the sun is white. So what could separate it into blue? What do we know about light and matter? What do we know about the atmosphere? Guide the thinking. Don't provide the answer. Make the child reason. Make them think through possibilities. Make them develop the mental muscles of reasoning. Make the distinction. Teaching what to think creates memorization machines. They know the answer, but they can't think about similar questions. They can't apply the reasoning to new situations. They can't figure anything out they haven't been told. Teaching how to think creates thinkers. They might not know this specific answer initially, but they can figure it out. They can reason about it. They can apply their thinking to any question. 8 fourth problems. Problem 4. We test memorization instead of testing understanding. Tests ask, what is the capital of France? What is the formula for photosynthesis? Who signed the Declaration of Independence? Questions that have one right answer. Questions that test whether you memorize the information. Questions that a computer could answer better than any human. Pause, but tests don't ask, why did Paris become the capital instead of another city? Why does photosynthesis work the way it does? What were the different arguments about signing the Declaration? Questions that require thinking. Questions that test understanding. Questions that reveal whether you can actually reason. They make the impact. So students optimize for the test. They memorize facts. They don't develop understanding. Why would they? Understanding isn't measured. Understanding doesn't improve your grade. Memorization improves your grade. So that's what they do. That's what we've trained them to do. Share Feynman's experience. Feynman served on California's Curriculum Commission, evaluating science textbooks, and he was horrified by what he found. Books full of facts, full of definitions, full of things to memorize, but almost nothing that taught kids how to think scientifically, how to observe, how to hypothesize, how to test, how to reason. Share his reaction. He gave a scathing report. He said these books teach children science, without teaching them anything about how science actually works. They teach what scientists have discovered without teaching how to think like a scientist. They create memorization machines who can recite scientific facts but can't think scientifically. Fifth problems. Problem 5. We prioritize coverage over depth. The curriculum must cover 40 topics this year, so you spend 1 week on each. Skim the surface. Move on. Can't go deep. No time. Too much to cover. Make the impact so children learn a little about everything and understand nothing deeply. They skim surfaces. They memorize key terms. They move on before developing real understanding. They become memorization machines who know a little bit about a lot of things, but can't think deeply about anything. If I can make the contrast, thinkers learn deeply. They take one thing, they explore it thoroughly. They understand it from multiple angles. They connect it to other things. They develop genuine understanding that transfers to other domains. Better to understand 3 things deeply than to memorize facts about 30 things. Share Feynman's approach. Feynman would spend months on a single physics concept, exploring it, playing with it, understanding it from every angle, building intuitions, creating mental models. Other physicists would cover more material faster. But Feynman's deep understanding meant he could solve problems they couldn't, could see connections they missed, could think in ways they couldn't. Make the point. Depth creates thinkers. Breadth creates memorization machines. We're choosing breadth. We're creating machines. Pause. Bring it together. So those are the 5 problems. We reward answers instead of thinking. We punish mistakes instead of treating them as learning. We teach what to think instead of how to think. We test memorization instead of understanding. We prioritize coverage over depth. These create direct address, and together these create memorization machines. Children who can recite, who can follow procedures, who can pass tests, but who can't think, can't reason, can't solve novel problems, can't create. Get hopeful. So how do we fix this? How do we raise thinkers instead of memorization machines? Let me show you Feynman's principles. The specific things you can do, as a parent, as a teacher, as anyone who influences children to develop thinking instead of memorization. Principle 1, reward the thinking process, not just correct answers. When a child solves a problem, don't just check if the answer is right. Ask, how did you figure that out? What did you think about? What did you try? Reward good thinking even if the answer is wrong. Praise creative approaches. Praise clear reasoning. Praise willingness to try novel methods. Make it concrete. You got the wrong answer, but I love how you thought about this. You tried something I've never seen before. That's excellent thinking. Let's figure out together where it went sideways. Versus wrong. Here's the right way to do it. Memorize this procedure. Share the impact are the first creates a thinker. Someone who values good thinking and isn't afraid to try. Someone who learns from mistakes. The second creates a memorization machine. Someone who learns to follow procedures and never deviates. Hacks of P, Principle 2. Make mistakes safe and valuable. When a child doesn't know something, celebrate it. Excellent, something you don't know yet. That means you get to learn something. Let's figure this out together. When a child makes a mistake, treat it as data. Interesting, you thought X, but it's actually Y. Why do you think you thought X? What made sense about that? What can we learn from this? A fact make the mindset shift. Mistakes aren't failures. Mistakes are experiments that give you information. I don't know, isn't shameful. It's the starting point of learning. Create an environment where children aren't afraid to be wrong, where they're willing to try, where they learn from errors. Share Feynman example, Feynman's father did this constantly. Young Richard would have an idea about how something worked, and his father would say, "That's interesting. What made you think that? Let's test it and see." That's wrong. But let's think about this together. I say make the impact that created a thinker. Someone comfortable with not knowing, comfortable with being wrong, comfortable with the process of figuring things out. Principle 3. Ask questions instead of providing answers. When a child asks why, don't immediately give them the answer. Ask them, what do you think? Why do you think that happens? How could we figure that out? Make them think. Make them hypothesize. Make them reason. Guide their thinking. But don't do the thinking for them. Make it concrete to a child. Why do boats float? A bad response, because of buoyancy. Objects float when they displace water equal to their weight. Good response? Great question. Why do you think they float? What would make something float or sink? Let's think about this together. Share what this does to you. The bad response creates a memorization machine. The child memorizes buoyancy and displacement. Without understanding, the good response creates a thinker. The child reasons, observes, tests ideas, develops genuine understanding. Principle 40, Principle 4, focus on understanding, not coverage. Don't rush through topics. Go deep. Let children explore. Let them play with concepts. Let them understand thoroughly before moving on. Better to understand 3 things well than to memorize facts about 30 things. Make it practical. If your child is curious about how plants grow, don't give them a 5-minute lesson and move on. Spend a month on it. Plant seeds, observe daily. Experiment with different conditions. Draw pictures. Ask questions. Develop deep understanding. Share the payoff. That deep understanding of plants transfers. They learn about observation, about cause and effect, about patience, about experimentation, about systems. That's thinking. That transfers to everything. That's valuable. Principle 5, teach through experience and discovery, not lecture and memorization. Don't tell children facts to memorize. Create experiences where they discover principles themselves. I make it concrete. Don't say things fall down because of gravity. Instead, drop different objects. Let them observe. Ask, what do you notice? What's the pattern? Why do you think that happens? Let them discover that things fall. Let them notice the pattern. Then introduce the word gravity as a name for what they've already discovered. If I share Feynman's philosophy, Feynman said, "What I cannot create, I do not understand." If a child memorizes that gravity makes things fall, they don't understand gravity. But if they discover through experience that things fall, and then learn that we call this gravity, they understand. They created the understanding through experience. It's real, it's permanent, it's usable. Share transformation story. Let me tell you about a family who applied these principles. Call them the Johnsons. Their daughter, Emma, was struggling in school. Good grades, she could memorize and regurgitate. But she wasn't actually learning, wasn't developing as a thinker. They pulled her out of traditional school, started homeschooling using Feynman's principles. Share their approach and no textbooks, no curriculum to cover, no memorization. Instead, Emma got curious about something and they'd explore it deeply. She wondered how bridges work. They'd spend weeks on bridges, visit bridges, build model bridges, experiment with structures, understand the principles thoroughly. She wondered how music works, months on music, learning an instrument, understanding sound waves, composing, experimenting. Share what happened in the first year. She learned about maybe 6 topics, deeply, thoroughly, with genuine understanding. A traditional school would have covered 60 topics, superficially, through memorization. The result of 5 years later, Emma is back in traditional school, and she's the best student, not because she memorized more, but because she learned how to think. When given a problem she's never seen before, she doesn't panic. She thinks about it, reasons about it, figures it out, because she's a thinker, not a memorization machine. I can make the universal point that that's what happens when you prioritize thinking over memorization. You create someone capable, someone who can handle the unknown, someone who can actually use their mind. Address the concern. Now, some of you are thinking, but my child needs to pass tests, needs good grades, needs to get into college. I can't ignore the system. I can answer honestly, you're right. The system exists. The system rewards memorization. You can't completely ignore it. But offer the solution, but you can do both. You can help your child pass the tests while also developing their thinking. The tests require memorization. Fine, help them memorize enough to pass. But don't stop there. Don't make that the goal. Make thinking the goal. Make understanding the goal. The tests are just hoops to jump through. The real education is developing their mind. Make it concrete as your child has a biology test on photosynthesis. They need to memorize the formula. Help them do that. But also go deeper. Why does photosynthesis work this way? What would happen if it worked differently? How did plants evolve this? How does this connect to what we know about chemistry? Pass the test. But develop thinking. Don't let the test be the limit of learning. Share Feynman's own experience of Feynman did this. He passed tests. He got good grades. He succeeded in the traditional system, but his real education happened outside the tests. In exploration with his father, in figuring things out on his own, in thinking deeply beyond what was required. The tests were obstacles to overcome. The thinking was the actual education. There's present the bigger picture, here's the bigger truth. The world is changing rapidly. When today's children enter the workforce, most jobs will be different from what they are now. Many jobs will involve problems we can't even imagine yet. Situations that require adapting, thinking, creating solutions that don't exist. Make the stakes clearer, memorization machines will be obsolete. Computers already memorize better than humans. AI already retrieves information faster than any human can. But thinkers will be invaluable. People who can reason about novel situations, who can solve undefined problems, who can think creatively, who can adapt. A direct statement, that's what your children need. Not the ability to recite facts, the ability to think, and you can give that to them. You can raise thinkers instead of memorization machines. Present the practical summary. Here's how apply Feynman's 5 principles. 1. Reward thinking, not just answers. Praise the process. Value good reasoning even when it's wrong. 2. Make mistakes safe. Celebrate not knowing. Treat errors as learning opportunities. 3. Ask questions instead of providing answers. Guide thinking. Don't do the thinking for them. 4. Go deep instead of covering everything. Understand thoroughly. Don't rush. 5. I've learned through experience and discovery. Create, experiment, observe. Don't just memorize. Make the promise to do these things, and you'll raise a thinker. Someone who can actually use their mind. Someone prepared for a world we can't predict. Someone capable of handling whatever challenges emerge. Tell final story. Let me end with one more story about Feynman. Late in his life, someone asks him, "What made you such an exceptional physicist? What made you able to think in ways others couldn't?" And Feynman doesn't credit his intelligence. He credits his father, those walks in the woods, those questions, that approach to learning. Share his answer. My father taught me to think, not to memorize. He taught me to question, not to accept. He taught me to reason, not to recite. That's what made the difference. Not being smarter. Being a thinker instead of a memorization machine. Our final challenge, that's available to your children too. That kind of thinking, that kind of capability, that kind of preparation for the future. But only if you choose it. Only if you prioritize thinking over memorization. Only if you resist the pressure to create another memorization machine and instead commit to raising a thinker. The Zum walk to center. The world doesn't need more children who can recite facts. We have machines for that. The world needs children who can think, who can reason, Who can solve new problems? Who can create new solutions? Who can adapt to unknown challenges? If I direct address here, your children can be those people. If you raise them as thinkers instead of training them as memorization machines. It's a final statement, so make the choice. Choose thinking over memorization. Choose understanding over coverage. Choose depth over breadth. Choose questions over answers. Choose reasoning over recitation. Raise thinkers. The world needs them. Your children deserve to become them. Thank you. And if you want to understand more about Feynman's approach to education, if you want more specific techniques for developing thinking instead of memorization in children, do me a favor. Like this video and subscribe to the Mind of Richard Feynman channel. We're exploring how to actually educate for understanding and capability, not just test scores. Join us. Let's raise thinkers together. See you in the next one.